Hello everyone, thank you for coming. Very happy to have you guys all come out for the lecture tonight. I hope you all grab some food. Feel free to grab more right now. So before I introduce our speaker for tonight's lecture, I wanted to formally announce the start of NEURO's first annual Brain Awareness Week. This is an idea that originally came about 9 months ago, and I'm very excited that it's actually becoming a reality this week. And I hope that you enjoyed today's talk, and you guys should all have gotten a program that we've been passing around, and I hope that you come out to more events throughout the week. So now I wanted to introduce Dr. Antonio Rangel, coming from Caltech. He's a Bing Professor of Neuroscience, Behavioral Biology, and Economics at Caltech. He received his PhD from Harvard and was an assistant professor of economics at Stanford from 1998 to 2006, as well as a research associate at the National Bureau for Economic Research. In 2006, he switched over to decision neuroscience and moved to Caltech, where he currently is a professor. He also recently served as a director for the PhD program for behavioral and social neuroscience at Caltech, and a co-director for the Brain Imaging Center. He's a founding member and a past president for the Society for Neuroeconomics. So Dr. Rangel's laboratory studies the computational neurobiological basis for decision making, and today he's going to be talking about the neuroeconomics of simple choice and explaining how the brain computes decisions such as choosing between an apple and an orange. So, Dr. Rangel.
Thank you for having me here. Let's do some basic housekeeping things before we start. First, I want to know who's in the audience. So, and you have to vote, okay? If you're an undergraduate, please raise your hand. Okay, if you're not an undergraduate, please raise your hand. Okay. Now, you have to choose a field, just so I know the distribution and a little bit to fine-tune the talk. If you're a neuroscientist, raise your hand. Okay. If you're a psychologist, raise your hand. Economist? Okay. Other? Okay, good. Thank you. This is very useful for me. When I normally give talks, I give two types of talks. I give very wide public lecture talks, who knows who's going to show up, or I give seminars to other scientists, okay? Today I'm going to try to give you a talk, especially because I have great respect for U of C undergraduates. I'm going to give you a talk that is somewhere in between. So, given this, I want also to invite you to ask questions during the talk. I've been warned, and having had undergraduates from U of C work in my lab, I know from first experience that you guys like arguing back, which I love. If I feel that we're running out of time, and I would put my social planner hat and move ahead, okay? Don't take it personally. But please ask questions during the talk. I think it's much more enjoyable than having talks at the end. Without more preamble, let's jump into it. A big fraction of the work that we do in my laboratory seeks to understand something extremely exciting. So I put an apple in front of you, I put an orange in front of you, I put a buffet in front of you. Okay, thank you for the example. And we want to understand what are the computations that the brain carries out from the moment you identify the decision problem to the moment you reach with your hand to put one of those things in your hand and bring it to your mouth, okay? How exactly does the brain solve this problem? Now, if you have any training in the social sciences, you may begin rolling your eyes and think, this could not get more boring than this. What people are going to do is they're going to compute the utility of the apple, the utility of the orange, and of course pick the one with the highest utility. Let's go and have dessert and stop listening to this crazy man, okay? I hope to convince you by the end of the talk that neuroeconomics is exciting because even a problem as simple as this has a lot of richness into it that we need to understand about how the brain processes this. And even if you couldn't care less about the brain, as many economists do, understanding the computational properties of how the brain solves this problem will give you a lot of insights into the underlying behavior, okay? Now, also, let's just make a compact. I am even more aware than you that this is not this, okay? And for my former self, I'm getting skinny, it's also not this. Okay? Simple choice. Simple choice. If you want to ask questions about how these things extend to self-control, to altruism, to this, let's have that discussion at the end. Let's just focus first on this simple case where we can do very basic control science to understand how the problem is being solved. Okay? The other thing I want to do is, because it's such an interdisciplinary audience, is to help you from the beginning locate where neuroeconomics fits into the field of knowledge. Okay? Now, this is the way I think about it. I have found this very useful throughout the years. Think of 3 tiers of understanding. One is the space up here of behavior where traditionally social sciences have worked, economics, psychology. At that tier, the name of the game is to write down models of how you think the behavior is being generated, utility maximization. I'll just give you an example, or more sophisticated versions of that. And then you validate, you test theories only with behavioral data. If your model can predict the behavioral data, win for the theory. If your model cannot, ideally, but this is not as often done in practice as it should, off with the theory, let's pick another one, okay? Now, if the theory predicts the data, the behavioral data well, but makes no sense whatsoever from a neurobiological point of view, who cares? That has been traditionally what has been done there. On the other corner are neurobiologists who traditionally have tried to understand how the brain is put together and what different areas generally do. But their main understanding has been, the main goal of understanding has been the brain. And behavior has been an afterthought. Only to the extent that it helps you understand a little bit or provides a little bit of insight about the brain, they have cared about it. Neuroeconomics sits at a sweet spot on the middle, okay? That is trying to do something that you may disagree, but I find very beautiful. And this is why I work on this area. It's trying to do the following. It's trying to ask, can we write down computational models of how the brain is solving different types of decision-making tasks? And what I mean by computational model, you will get more of a feeling as we go along, is something very simple. What are the variables that the brain encodes at the time of facing the decision, and how those variables interact dynamically to produce the behaviors that we observe, the subjective states, etc. That's question number 1. But question number 2 is, how are those computations implemented and restricted by the underlying neurobiology? Okay? And I find this beautiful because a good theory at this level, which is the level at which neuroeconomics operates, has to pass 2 tests. It has to be able to explain the behavior as accurately as in the standard social sciences, but it also has to provide theories that account for how the brain operates. If I tell you at this level that the behavior is generated doing X, Y, and Z, but then I look at the brain, and the brain does alpha, beta, and gamma, that theory sucks. And you have to throw it away. Why is this beautiful? Because if this program over the decades is successful, it's going to be able to really unify the behavior and the social sciences. And you will have a theory of human nature, a psychology, a theory of decision making that predicts behavior well, but is also rooted on the biological machines that we are at the end of the day. Does that make sense to you? Okay. I just want to do this. By the way, just as a parenthesis, I have to tease my fellow economists. I have a PhD in economics, so I can tease the economists. I'm allowed. Do not fear, you're not going to have to learn neuroscience. This is not about changing how economics is done, but this is about making sure that the models that you use up there are not ridiculous from the point of view about what we know about the underlying neurobiology. Okay. So today I'm going to spend the rest of the talk telling you about work that we have done in my laboratory about seeking to understand how do you choose apples versus oranges. Okay? And in order to organize the research, I find the following diagram useful, and I hope you do too. Suppose that I put the apple and the orange in front of you, at a very high level, it's not a model, it's just an organizational framework. We think that you can think of there are three things that need to happen. First, you assign a value to both things. Somehow, and this is where things get very interesting, that value gets compared to select one of those two stimuli, and then somehow that comparison is able to generate a motor movement, either your hand moves or your left hand moves or your right hand moves. And that's how we're going to split. I'm going to split the material that I'm going to tell you. First, we're going to spend some time asking the basic question is, are there dedicated valuation systems and what are the properties of those value signals? How are these values computed? And that's very important because under this general framework, if this framework is correct, whatever you assign values here is going to have a big impact on when you end up choosing. And second, how are the values compared and what are the properties of those systems? Okay? So let's just jump into it. Question number one is the first question we started in the lab. This is about 6-year-old research now. Are there dedicated valuation systems? Okay? If this model is correct, there better be either an area, a set of units, or a network in the brain that at the time you're making a decision encodes the value of a stimuli for the purpose of guiding the choice. For the social scientists, it encodes decision utility, okay? And we're going to use, by the way, to show you a different decision-making task. And first, we show them 3 classes of items, either this type of tacky Caltech paraphernalia, foods, or monetary gambles. For each one of them, they make a bid, just as before, so it gives us a measure of the value of each one of those items. Those measures are in a common scale. We can check it because then we can ask in the task that follows whether the subjects are equally likely to choose them as a function of the willingness to pay or bid that they reveal, and they lie on top of each other. So they are in a common scale. And what then we do is we put them in the scanner, and every trial they ask, do you want to choose an 80% chance of getting that particular item, the item shown in that trial, or a constant amount of money, think of it as the price, that is the median value over all of the items. Notice that when you're solving that problem, according to the organizational framework that I showed you, you have to assign value to this, you have to assign value to that and compare them. But across time, that is constant, so all of the variation in neural activity that we can measure is going to be driven by the value of that. So you can ask, is there an area of the brain here that correlates with the measured values for each one of these items in these different decision-making tasks and for different classes of items? And what you find is that these areas, especially of this area here, and this is the intersection of all of this, these areas of ventromedial prefrontal cortex, some people call it the medial prefrontal cortex, always in this task, regardless of the class of stimuli, correlate with the value of the stimulus. Does that make sense? Okay. There are now dozens and dozens of studies that have looked for these value signals in very different contexts and domains. And every time the experiment has 2 features: A, the details of the scanning and the scanner are kosher, and B, they have a good behavioral measure of value. They find that this area of the brain encodes that value signal. By the way, there are other areas of the brain that correlate with value reliably in some but not all studies. This one always does. The posterior cingulate cortex, the ventral striatum, sometimes it does, sometimes it doesn't. And it's a huge open question, in my view, in the field of what exactly are they computing. We don't know yet. Questions? Yes?
Yeah. When you say it's correlated, so when you were bidding like $100 for Butterfinger, the area
you bid $100 for Butterfinger? I'm willing to fly you to California. I'm going to run quite a profit with you. Not with your parents, but with you. Yeah, sorry.
That area of the brain was more activated? Is that the...
The way to think about it is this area of the brain has a baseline level of activity. Then a stimulus appears and you have to make a decision. Say, yes, no, I want to eat it, or I want to buy it, or how much will I bid for it? At that point, there is a neural response that goes away a few seconds after. The size of that response, okay, is what is correlated with the value of the thing. It's in the change in signal the change of activity that this OFC,
So the $100 bid would have a bigger change?
than the 50, and that would be bigger than the 30, and the 10, etc. It would be linear. Let me tell you one other thing that you may find interesting. One interesting question for us about these value signals and the role in decision making is how quickly do you compute them? Okay? And let me put this in context. There are these very famous psychologists that have argued that the moment you notice the buffet consciously, you were doomed. You had already made your choice. And that everything that was happening somehow was epiphenomenal. You guys have heard those plans? Yeah. Okay. That assumes that all of these processes are working extremely fast at thresholds that are below consciousness. Okay? So one interesting question to start addressing this for us was, okay, how quickly do these value signals show up in the brain? I'm controlling the time, I'm looking at the time, and I have a bunch of really interesting stuff to show you later, so I'm going to just say one thing. We can do versions of the experiment that I have just shown you with something called EEG, okay? Electroencephalography, which is a different technique than fMRI that we use. That has the advantage that has much lower temporal resolution. I can resolve the signal spatially in the brain much worse, much more poorly, but they have, arbitrarily better temporal resolution. And what we do is we run the same experiment with the same subject with EEG. We are able to localize the signal, the source of the signal that we measure on the scalp with that technique, using the fMRI data that we have collected with the same subject. And then we can ask, for example, in a region like the orbitofrontal cortex here, it's very similar to these BMPC regions, how quickly do these value signals arise? And what I wanted to tell you is that in this study, we find, and we have replicated it, that by about 400 milliseconds, the value signals for these simple choices are already there. And they seem to come online and stay there until about 100 milliseconds before you make your choice. And then they disappear. Does that make sense? They are incredibly fast. Now, 400 milliseconds, you are conscious of the stimulus, but I would argue a little bit after the fact. So you are computing the values very, very fast. Okay? We'll come more to consciousness in a second. Questions?
Does the size of the delay response track value?
Just as these are exactly areas that have that property. Just let me tell you what this diagram is. ERP is event-related potentials, 400 to 550 milliseconds after the stimulus shows up, 700 to 800 milliseconds after. Green, blue, and the two blues are localizations of these value signals with fMRI. What I show you is that all of these blobs with different techniques in different experiments have the property that the value signals are there, just like we were discussing before. It's just that now I can tell you exactly when they appear. They appear by 400 milliseconds.
Right. I was asking if you also see it if you also see the modulation by value in the EEG.
Yeah, those are signals.
Okay.
At 400 milliseconds, these areas respond much faster than that. So you went to a change from baseline the moment the stimulus shows up, much faster, by about 90 to 100 milliseconds is there. But those that change in the signal doesn't contain information about value. Information about value only shows up about 400 milliseconds later. Okay. Let me jump to the second. I assume you want me to stop at 8:05. Okay. Let me jump to the second question about how these values are computed. Now, you may think, if you stop to pull your intuition for a second, that when you see a bottle of water, a Coke, an apple, the way you compute the value that guides the choice is by retrieving it from memory. You have eaten apples in the past. Maybe by trial and error, you have learned the value of an apple and just retrieve it and it shows up there. There is a lot of hints that we had that led us to think that that is actually not the case. And I'm going to show you what we think is going on and the preliminary lines of evidence supporting this. So this is what we think happens when you see an apple. It's not that you see the apple and immediately you retrieve the value. Instead, you're going to compute the value online. In particular, what I think is going to happen, you're going to see a stimulus, and the first thing that's going to happen is you're going to extract perceptual measures of the stimulus. What's color, contrast, orientation, blah, blah, blah. The other thing is that over time, what you have learned is associations between a stimuli that has those perceptual features and particular outcomes that you care about. So what is the probability that how do different colors affect the probability of getting something sweet, the size of the calories, the amount of acidity, etc. And you do it for every perceptual feature. So now, given that you have done this and you have learned these mappings, you can predict the level of sweetness, calories, acidity, etc. that you're going to get, actually a distribution over that. Over time, you have also learned how each one of these things, these attributes, affect your reward that you experience, okay? And now, therefore, let's say that you think this is going to give you 3 units of sweetness, you can multiply that by the value per unit of sweetness that gives you the component value of sweetness, etc., and then you add them up. Does the algorithm make sense? Is that high level? Okay. Now, this is very useful for one reason. Suppose that I show you a new item that you have never seen. Unless it's a completely alien artifact, you're going to be able to assign value to it very quickly. This algorithm is going to allow you to do so by generalizing from previous experience to the things that you encounter. And that's why we think the brain does it this particular way. Yeah.
Is there any reason to think that there aren't sort of more levels here? So now you condition. So now you have some sort of outcomes of outcome features, and you see what the conditional probability of those things being the case is based on the outcome features, and so on and so on and so on.
I think your question is a very important one. I'm gonna
Sorry.
answer in a slightly different way that you posed it, but I think it's the same idea. We think that something like this is going on. We have no idea. No idea. To me, it's one of the most interesting open questions in the field. What is the list of things that come here? And what is the list of comes here? And how exactly is this map constructed? Okay? I mean, I could write very simply models that do this mathematically and program them in artificial intelligence. They will learn things. But we don't know if that's actually the way it's doing it. And the way, by the way, the brain has a tendency, especially when you go to perception, to code things in k-dimensional inverse cluster to the alpha space that makes no sense to us, but makes a lot of sense to the brain. So this is a huge open question. And I put your question there because it may be, for example, that it's not only perceptual measures, it could be that you can retrieve memories. And that episodic memories of particular episode of consuming that period get activated here. They don't really control outcome features, but it's something here in between that maps to value, etc. We don't know. And by the way, it's even more interesting than that, because what may happen is these things may happen at different times, at different time scales. It may be that doing these perceptual associations is faster than retrieving those episodic memories, and therefore, depending how much time you have to make the decision, different things will be weighted differently. You immediately see the realm of possibilities. Interesting, we don't know. Yes?
So, shouldn't there be something that accounts for something other than perceptual qualities? Because, I mean, there's some mechanism by which I could put a real apple and a fake apple, like a plastic apple in front of you, and then, have them be arbitrarily close in color and whatever other perceptual qualities are listed there, but you'd still be able to differentiate between the two.
So 2 comments about this great question. One is what I just told him, that there are probably other things, potentially. But the other thing is that I would argue, and it's a more important part of your question, that if you really have all of the features that the brain is using here, you will salivate just as if you had the real apple in front of you. And to the extent that you don't, my prior, of course, happy to be proven wrong, but my prior is that you are missing some perceptual features. And intuitively, the proof is in the pudding. You know that it's something fake. I don't know, have you guys been to these Japanese restaurants that have the fake sushi? You know it's fake, even though they try to do a very good job. Yeah.
My question, I guess, is about the time in the decision-making process, because you say it's 400 milliseconds, right? And I'm wondering about the difference between different individuals, because some tend to be a lot more decisive and impulsive, and others tend to take longer time to deliberate, like the outcome. And I'm wondering, like, what does that mean here? Does that mean that, like, maybe their feature values are generated slower, or maybe their feature values are going to be like equal? And I'm just asking about your opinion, because obviously it's a complex question.
It's a great question. First, when I tell you approximately 400 milliseconds as the average on the group. There's some variation. And normally these studies don't have enough power at the individual level to pin down precisely with sufficient precision the individual times. But if you do that with the energy estimate, you see some degree of variation. Let me say something that is more interesting that goes to the core of your question. And it relates also to what he was saying. If this algorithm has merit, and I'm going to show you a second that it does, or I think evidence that I think it does. But if it has merit, you can ask the following question. Are different features, for example, different levels of types of outcome computed at different times? Okay? And the answer is yes. We have done another series yes under review. But you can ask, for example, we have done experiments with food, just to give you a flavor for this, in which we can measure two attributes that matter a lot, especially when people are trying to engage in dietary control. How tasty and how healthy are the foods? Okay? And we can show with other techniques that the value, the signal, the component of value given to attribute, on average, shows about 80 milliseconds before the health component. Not only that, and this is why I'm telling you this, when you look across subjects, you can construct an index of how good they are at dietary self-control. About 40% of the variance on that can be explained by difference across subjects of how much faster they compute the taste information than the health information. The slower you are at computing the health information relatively to others, the more likely you are to exhibit bad self-control. So this point that you are raising is very important because differences in the individuals, for example, if you're someone that pays more attention naturally to the attributes that are slower to compute, you're going to show your value signals are going to show up at different times, etc. Yeah.
Have you found any differences in variance between when you see increased firing in the areas of the brain that you're associating with value computation, and then the time that it takes for the motor selection to set in?
We haven't done that. That's very interesting, actually. The prediction that I would have is that the longer it takes for you for the value signals to reliably show up, the longer your reaction times are going to be by approximately the same lag. But I haven't tested that explicitly. That's a really cool idea. Okay. I'm trying to select what may be of more interest to you. Instead of showing you a lot of stuff, I like the way he's doing. I'm going to do one thing with your permission. I'm going to skip the evidence for this for a second, for this model. And I want to show you something about the comparator, because I think it's going to have great interest to you. And if we have time at the end, I will come back to show you the evidence for that. Okay? So let's talk a little bit about how values are compared. And we have proposed before a model that does the following. And let me motivate it with some physical comedy just for a second. When you arrive here, okay, oh, let me arrive from the other side. It's actually important. The other side is important. So I'm not when you arrive here, you probably did something like this. Okay, this is an accelerated version. Okay. Now, many models in psychology before this model implicitly assume that you did the following. You came, you look at empty space, and you did this. Okay? We want to understand how the values get compared and what is the role of that attention. Why is it that your eyes keep moving across the text? Okay? That's part of it. This model is going to account for that. It's called the attentional drift diffusion model. Let me explain it. This has some beautiful predictions that you may find interesting. So the idea is the following. You start, think of the following experimental trial. You start, I show you two items. You are able to fixate to them. You have your hand on the keyboard, you press either the left or the right button. Okay? When you're ready, you press. That's your choice for the trial. You make hundreds of choices. At the end, we select one of the trials and we implement it, and you have to read whatever you chose. During that time, we collect eye tracking. We know you're fixating. And importantly, we use an independent task to measure the value that you assign to things using a bid or a liking rating or something like that. So we know that independent measure of value of both things. Now the question is how are those independent or latent values going to be compared to make the choice? That's what this is explaining. So the idea is the following. This is time. Time 0 is when the stimuli appear. The final time is when you make the choice. The model assumes that you're going to compute a relative value signal, that your brain is going to compute its best guess of how much better is left than right at any instant on time. If the signal gets high enough, it crosses a pre-specified barrier up here, you choose left. If the signal gets low enough, you choose right. Okay? Are you with me? Now, the key question, of course, is how that signal evolves. That signal is going to evolve as follows. It's going to have noise, Gaussian noise, okay? Independent across time intervals. But the key thing is that the fixations are going to matter. Model predicts, suppose just for the purpose of illustration, that you fixate left, right, left. When you're fixating left, the model assumes that you're climbing towards the left barrier, or the change in the value, the relative value signal range, is proportional to the value of left, listen carefully, minus theta, the value of right. It's not value left minus value right, it's value of left minus theta, the value of right. Okay? If theta is less than 1, you are weighting more the thing that you're looking at, in this case, the left thing. The model also assumes that when you look right, you're climbing towards the right barrier with a speed value of right minus theta, value of left. If theta is equals to 1, fixations don't matter. You're always moving towards the barrier with the relative value. But if theta is less than 1, the fixations are critical because they affect how you're climbing. To give you an example, suppose that the two items have equal value, let's say a value of 0, but you are fixating left. Towards what barrier are you climbing? Left. Left. Is there anyone who doesn't see that? Okay. So the model kind of inherently predicts that there is going to be a bias towards the thing that you're looking at. Yes? Now, just two extra things. The model assumes that the fixations are random. There may be a special bias. Let's say you may be more likely to look left first or left longer, but they are not correlated with value. And basically, you can think of the model as you draw a first fixation randomly with its length, and you run the fixation unless the model has crossed the threshold, then you continue doing that. Okay? Now, this model has 3 free parameters that we can estimate based on the behavior and reaction time data and the eye tracking data. But more importantly, it makes really, really wacky predictions about how where you fixate should affect what you choose and how long it takes. So let's see how well the model does. Let's see if it's really a description of the computational algorithm of how values are compared. I'm going to show you a bunch of graphs. These graphs have 2 things I want you to notice. First, black is data. Red are predictions of the model out of sample. What we do is we split the data. Half of the trials we use to estimate these 3 free parameters. And the other half of the trials we use to predict, trial by trial, given the fixations and the values of the thing that we have measured, what should be happening. Everybody with me? Let's see how well the model does, and let's do some of the wacky predictions. These are just some basic psychometrics that are not particularly interesting, but I just want to show you that they match well. But this is, for example, if you plot how much better is the value of the left minus the right as measured by these independent liking ratings, you get a nice psychometric choice curve. The probability you choose left increases as a logistic curve, and it matches very well. This is a measure of difficulty. How much is the difference between the best and the worst item? These are easy trials, these are hard trials. This predicts that reaction and it tracks it very well. This is the same thing with a number of fixations. There is a little bit gap there that has to do with a limitation of the fitting procedure. This love is well. I'm happy to talk to anyone who's curious about that. But here comes the more interesting things. Now, if you are with me, the model predicts that the last fixation should be shorter than any other fixation. Why? Because think about what I told you about the model. You draw a fixation and a fixation duration, and you run through it unless you cross the barrier. So the last fixation is one in which there was a stop in the middle. It has to be shorter. That is the case. This is more interesting. Please look at my hands. The model predicts the following, which is, suppose that you're going to choose left. You're going to cross this barrier, and you condition on that. And then you ask, how long has to be the last fixation as a function as of the beginning of the last fixation, how much longer you can look at the other thing. Okay, so you know you're going to choose here. You look at the first fixation, at the beginning of the last fixation. You measure how long that last fixation is, and you ask how does that length depends on the relative duration, extra duration which you had looked at the other thing as of the beginning of the last fixation. Because of the bias, the more you had looked at the other thing, the more you had climbed on average away from that barrier. The more distance you have to make up, the longer that fixation should be. There it is. Same slope. More interesting. Look at me again. Sorry for a second. You arrive at the convenience store. There is no law of nature that I know that precludes you from doing this. The two items are there. You do this. You do this. Now you have seen the second thing. Then you choose this without looking at it. Yes? Remember, your hand is on the keyboard. There's no reason why you need to look at it. And yet the model predicts that there should be a bias towards choosing the last thing that you saw. Not the first, the last. Okay, because at the last fixation, you're climbing towards that thing. And in particular, so you plot the value of the last seen thing minus the value of the other thing, and you ask what's the probability that the last fixation was to the chosen item. The model predicts a curve like this. That's exactly what you see. It's a big bias in value. Okay. There's a marketing person in the audience. Get your person to look at the last item last. Let me just give you one extra thing, and then I'll move on from this. The model predicts the following. You take every trial, and for every trial you compute how much extra time did you spend looking at left than at right. So for example, there is you spend 600 extra milliseconds looking at left and at right, and vice versa. The model predicts that it should be a very sizable, about a 40% choice bias as you change the relative duration of the fixations. We remember our orthogonal, and there it is. It's a 40% bias. Okay. So the bottom line of this is to show you that this algorithm is able to account quantitatively for all of these patterns in the data that are quite sophisticated with great accuracy. So we think because of this, and then because this, we can, for example, estimate the model in the case of 2 items and predict the same patterns in the case of 3 items, and do a bunch of things like that. That is a good computational description of whatever is going on the comparator process and the impact that attention plays on it. Okay? Now, if you are with me, here's an interesting implication of this. It means that if you come to a store and somehow you change the light or you do something to get you to look more at one of the products than the other, and the product that you move your attention towards is appetitive, you will bias choice towards that. You guys see that? We have done those manipulation experiments, and that works. Now, before you think you're doomed by the marketeers, the model also predicts the following. If you have a crappy product and you get people to look more at it, you're less likely to choose it. And we also can show that. So thank God we're not doomed. You know, they have to have a good product, but conditional for that, they can change the degree to which the choice is influencing that direction. I'm almost done. I just want to show you 2 more things. I want to link back this computational model back to the brain just for a second. So that was very cool, but it had nothing to do with the brain so far. It was completely an independent thing. Then we want to ask is, can we link this back to the valuation signals that I've been showing you in the beginning? And in particular, where we hypothesize is the following, which is, this is again a repetition, a schematic repetition of this attentional drift diffusion model. And what we think is that there is an area that implements the comparator that if I had more time I will tell you about, But what we think is that this area takes as an input a relative value signal. A relative value signal that looks like value attended minus value unattended. And that's what guides this. Okay? And what we did to test that is we basically ran in the scanner the same idea of experiment with the eye tracking that I showed you, but it's slowed down to a crawl so that we could use the neuroimaging techniques. And then we asked subjects where to fixate. It's a causal experiment. So for example, in this run, it's a trial in which they have to choose between these two items, and they were always asked to fixate on the red thing. And then we have independent measure of values, and we can ask, are there areas of the brain that always correlate the response at the time of decision with the value of attended minus the value of unattended? Okay. Yeah. I'm passing out of slides. Don't feel that I'm shortchanging you. I just want to have flexibility about where to go depending on your interest. I just want to show you one more picture and then I will conclude. We have done a lot of work also trying to understand where the computations of this attentional diffusion model are implemented. In other words, where do the ventromedial prefrontal cortex signals of value get passed to for being integrated and passing the information to the motor cortex that move your hands. And it's a network that includes this dorsomedial prefrontal cortex, which is basically about 2 inches below where my finger is, and this bilateral inferior parietal lobe. Okay? Those areas have multiple markers, and if you're curious, that's the paper that you can read, of implementing the comparison. At the time of decision, they seem to be receiving information from the BMPFC. The total activity correlates with the predictions of these comparator models, and more importantly, and this is the coolest thing, if you're going to make a left choice, they seem to pass information to right motor cortex that control the left hand at the time of decision, and vice versa. Okay? So it has all of the markers. We think that we have only scratching, but we have begun to nail this. Okay, let me just conclude. In terms of findings, okay, what I want you to conclude? We think that there is now very large evidence that this ventromedial prefrontal cortex compute value signals at the time of decision making. I haven't shown you all of the controls, so this is a little bit of a leap of curiosity that you have to take for encoding in memory or for reading more through attribute evaluation. We also think that those value signals are causal. There are experiments now out there from people at MIT and Stanford that show that if at the time of choice you mess with the signal, for example, you bring it up or you inhibit it, you change choices accordingly. So we really think that this signal is causal. So when your wife complains that you do something, you can tell her, sorry, honey, my BMPFC made me do it, and you have a voucher from me that this is a completely kosher excuse. Sorry. We think that this stimulus valuation is computation extremely fast. It's attentionally modulated for the reason we have described. And one experiment that I skipped, but that you may be curious, you need to be conscious of the stimulus. Okay? If I flash you the stimulus, and I ask you to make decisions, your visual cortex sees the stimulus, and you can prove that, but you're not aware of whether you're seeing an apple or an orange, these BMPFC signals do not show up. You need to be aware of the stimulus. And that then these comparator processes are consistent with the attentional diffusion model implemented in this network that I showed you. Another thing I didn't show you is that one interesting question that you could ask, for example, is the following. This is if you are somebody who cares about the processes interested. Does the brain do the following? Suppose I put the apple and the orange, and you have to do left hand apple, right hand orange. You can make the choice in a stimulus space. Ask yourself, apple or orange? Okay, apple. Okay, I need the right action, and only then you do it. Or you can do the choice as apple or orange. Okay, value 2, value 6. Action left 2, action right 6. Okay, which action do I take? You can do it in action space. It turns out that the choice is made in action space, at least in the class of tasks that we have looked at. You're really choosing over multiplies. You can also nail that. Anyway, just wanted to remind you of this, that this kind of research if you're interested in it, has this kind of, is trying to integrate this behavior with this neurobiology by trying to understand what are the algorithms, the computational processes that are being used to make different kinds of decisions, explain behavior, and understand how they are implemented and restricted by the underlying neurobiology. Thank you. Any questions? Yes?
The information about your eyes being fixated on one product or one stimulus or the other, how does that work for if you're driving to the store and you see like 3 advertisements for one brand of something and 1 advertisement for another, and then when you approach it and you have various eye fixation on each product, does your previous exposure to one product rather than the other also?
We don't know. That's a very good question. I mean, I'm not trying to be evasive. Remember, part of the art of the science here is to make things simple and tractable. So in all of our designs, we take a lot of interesting things out, including that. Okay? But it could be interesting, for example, that suppose, I mean, you can even do it differently. Let me just kind of operationalize it slightly different. I bring you to the lab, I show you 2 items, and you make a preliminary choice in your head. And then I show you the actual product. So that changes the algorithm and the bias of what you're going to choose. That's the way I would, if you were in my lab, I would investigate it. I don't have data on it. I wouldn't be shocked if it doesn't. I don't have data on it. Yeah. One particular mechanism, by the way, in which that could operate is when you see the ads, it may affect your attention. And then even if you were to use the comparator algorithm, because of the impact of the attention, that may affect how you choose. One extra thing, sorry, just the last thing, and it relates back to her very interesting question. We have done experiments with dieters in which we ask them to choose whatever they want, and either choose normally, or to choose whatever they want, but during the choice pay attention to health. We kind of cue them to think about the health of the items. And what we find is that that changes the value signal that they compute on their choices to reflect more health. So there's a lot to what you're saying, I just don't have clean data on it.
All right, we'll take one more question, and then feel free to come up to Dr. Rangel afterwards for one-on-one questions.
Are there any other factors you think affect that comparator function besides attention? Are you testing any other hypotheses on that?
Yes, but they're hard to disentangle from the component evaluation. So let me give you an example. There's a postdoc in my lab who studies a version of what we call complex choice that has to do with altruistic choices, sacrificing resources for self versus other. And she's very interested in understanding, for example, first, this comparator algorithm also describes those choices, and the answer is yes. But interestingly, is the speed at which the information for the 2 things shows up is different. So for example, is it information about the self showing up faster information about the other? And does that, like in the diverse case that I told you before, reflects, you know, how altruistic you are and how long it takes you to make an altruistic choice? And the answer is yes. So there is a lot of detail there that you can change. Let me give you another example that we're investigating, and we have some preliminary data on this. Suppose that you come to a store, you always go to the same convenience store. And every time you go, your favorite item is on the left. Doesn't matter what you're feeling in the mood that day, on the left. On the left, okay? We hypothesize that if that happens a lot, your attentional system will no longer be random. It will kind of zoom on the left, and then maybe just check on the right. And that's indeed what happens. The fixation patterns change a lot. But then the rest of the algorithm goes through, and that's how it affects the choices. Thank you very much.